We are continuing reviewing for Unit 2. This is the third video, and it's the second part of the practice test. Question 13. This is, I think, the fourth time now we've done this type of question on the review. If the point 4, -9 is on the graph of an even function, even, remember, xy becomes opposite of x. Why? Because we're reflecting over the y-axis. Y doesn't change. So 4, -9 is going to become -4 and -9. Notice that the first coordinate changed, but the second one did not. Part B, 4, -9 is on the graph of an odd function. That's when your original ordered pair, everything is going to switch because you're rotating around the origin. So the 4 is going to become -4, and then -9 is going to become +9. Right. Y equals 1 divided by x plus 3 minus 4. We're supposed to graph it. I know that my parent function is 1 divided by x. That's a graph that looks like this. So I have asymptotes, and I'm moving in this one 3 to the left because x lies in the equation, and 4 down. So I'm going to go 3 to the left and 4 down, and I'm going to draw asymptotes there. And then I'll draw my curves. Look at the graph provided, write an equation for f at x. I know that this is an x squared equation. Let's move 1, 2, 3 to the left, and 1 down. Therefore, in the equation, it's going to be x plus 3 and then minus 1. All right. We're going to write a simplified expression for the inverse. Remember that this means inverse. And state the domain and range. All right. So my first step is to switch x and y. So that's going to be x equals the square root of y minus 6 plus 8. And then solve for y. All right, I'm trying to get everything away from y, so I'm going to subtract 8 from both sides, and I get x minus 8 equals the square root of y minus 6. I can't solve for y when it's stuck under that radical, so I've got to get rid of the radical by squaring, so I've got to square both sides. And I had told you guys you can leave that in parentheses. Okay, all right. I'm going to move up here. I'm going to add 6 to both sides. So I get x minus 8 squared plus 6 equals y. And I am fine if that is your simplified expression for the inverse. This tells me a lot. It tells me that I have a quadratic that is moved to the right 8, 1, 2, 3, 4, 5, 6, 7, 8, because x lies in the equation, and up 6. So I have a quadratic that looks like that, which tells me all quadratics domain is all reals, and my range starts at 6 and goes to infinity. Or I could say y is greater than or equal to 6. Look at the function below. Graph the inverse. In order to do that, I'm first going to list all of the ordered pairs that each of these dots represents, and I'm going to go in order. I believe that this is a 10 by 10. 1, 2. Yes. -10, 1, 2, 3, 4, 5, -5. So -10, -5. It's my first ordered pair, and then this would be -8, +5, negative 5, 0. And then negative 3, negative 2. And then negative 2, positive 2. Negative 1, negative 9. And then positive 4, negative 3. And what I need to do is I'm going to have my new set of ordered pairs where I'm going to switch x and y. So negative 5, negative 10. 1, 2, 3, 4, 5. Negative 10. And then I have 5, negative 8. And I need to connect as I go. And I have 0, negative 5. And negative 2, negative 3. Hmm. 2, negative 2. And then negative 9, negative 1. And then negative 3, 4. Okay. Suppose that f of x is 4x plus 7, g of x is 1/4 x minus 7. Use the inverse function theorem to show that f and g are not inverses. So that the inverse function theorem says that f of g of x equals g of f of x, and that equals x. So if this is true, then f and g are inverses. So let's try finding f of g of x. I'm going to take this and put it right there. 4 times 1/4 x minus 7 plus 7. The 4 gets distributed to both. X minus 28 plus 7. So I get x minus 21. Well, that does not equal x. So f at g of x does not equal x. So they are not inverses. It doesn't even matter if it equals g of f of x. It doesn't equal x. So they are not inverses. Okay, so let's start looking at the keys now. It says sketch the following functions. I know that this is a V-shaped graph. This is U-shaped. And this inverse. Right. Write their domain and range, and if they have asymptotes. Domain is all reals. Range, y is greater than or equal to 0. Same thing with the quadratic. Domain is all reals. The range is y is greater than or equal to 0. Here, my domain x cannot equal 0, and my range y cannot equal 0. And it's understood then that it can be anything else. But because x and y have this stipulation here, we have asymptotes. So this is the one graph that has asymptotes at x equals 0 and y equals 0. Right, 3.2, look at this at the graph of y equals x and its image. What is the translation? Right. Because it's linear, we could say that this was moved. It looks like it hits it down here. Gosh, it kind of looks like it goes here at 7 or here at 7. So we either moved to the right 7 and didn't move y, or we moved down 7 and we didn't move x. It's one of those two. Suppose a transformation. Oh, this one we've had several times, and I keep giving it to you because it's always one of the most missed questions on the test. We're going to apply this transformation to this graph. What are the equations of the asymptotes? My original asymptotes, since this denominator cannot be 0, 2x minus 6 cannot equal 0. So 2x cannot equal 6, so x can't equal 3. Therefore, my original asymptote is x equals 3. Well, if x can't be 3, so we put an asymptote there. If this is never 0, then y is never 0. So we have an asymptote there. Those are my original asymptotes, and then I move them. The x asymptote goes minus 2. So my new asymptotes are going to be, all right, new asymptotes. X equals 3. 3 minus 2 is 1, so x equals 1. 0 plus 3, y equals 3. Let's prove that this is an even function. That means I'm going to use my even test, that f of x has to equal f at negative x. So my first one, f of x, is simply 6x squared plus 5. F at negative x is 6 times negative x squared plus 5. Negative times a negative becomes a positive, so that just becomes 6x squared plus 5. They equal each other, therefore they are even. All right, I think this next question, it's the 5th time now we've done this question. You have the point 54. What other point must be on the graph for it to be an odd function? That's where we take x, y, and we rotate so they both change with odd. So that becomes negative 5, negative 4. For even, we just reflect over the y, so only x changes. So that's negative 5, positive 4. All right, I've got a scale change applied to this. So 2 times x, which means in the equation it's going to be x divided by 2. 5 times the y, so 5 is going to go on the outside. That's going to be my new function. Number 10, if I stretch horizontally by a factor of 4, scale change, remember, the rule never lies, so that's 4 times x. Horizontal is always x, vertical is always y, so that would be 2/3 y. On this page, I'm going to say do 11, 12, and 15. 11, you're going to put 20 into P, so you're going to put a 20 here and here. And so we have P at 20. When we put the 20 there and there, we're going to have 2 times 20 squared minus 5 times 20 plus 9. And we get 709. And so now we're going to put 709 into the m function. So m at 709 is 4 times 709 minus 2, which is 2,834. Okay. 12 is like the first one we did on the practice test, where you're going to put r into q, and you've got to be real careful with signs. So 2 times 3 minus x squared plus 4 times 3 minus x.